Anybody have their unit 0 notes or unit 1 notes out? What's it say calculus is? What is calculus? Oh, you didn't write it down. Massive change. Look, let's start talking about the massive change. Let's start getting into calculus. Let's get introduced to this word that you've probably heard before, but have no idea what it is, a derivative. Okay? All right, cool. 3 to 15, what's the change? 12, good. How'd you get that? Kind of figured it out, or you can subtract. You look at it on like a one-dimensional kind of number line, you can see it's the distance between the two, right? You say I went over 12. Or you can look at it on a number line here from 3 to 15, and you're like, yeah, you went up 12. Cool with that? 5 to 9, 4. Cool. So we can subtract numbers to get change. We know that if we went in the other direction, like 15 to 3, that you'd be going like to the left, or you'd be going down, and you'd say the change is negative. You guys are cool with that? You guys would confidently say like 3 to 15, that's more change than 5 to 9, right? This wins, hooray. But we are not going to just talk about change of just two numbers. We are going to focus our attention on the change of functions. Now, functions aren't just like y coordinates. Functions, graphs, have x coordinates and y coordinates. It gives some context to our location. It gives context to our y coordinates. So we won't just see 315. We'll have like an x coordinate that'll give us 3. We'll have an x coordinate that'll give us 15. Cool? Cool? So the question becomes like, if I gave you more information and I gave you a function that had x and y, and we got this change 3 to 15, and you got this change 5 to 9, would you still answer the same way before? That from 3 to 15, there's more change than from 5 to 9. Why don't you talk about that? And if you're not sure where to start, let's just plot the point. Okay? Go ahead. Ready, set, discuss. One, 3, 7. No. Well, that works. You know what? That's fine. And then over here, two, 5, 3, 9. All right. So I heard a word I liked hearing, where people are like, you know what? You do go up 12, but you go up 12 over the course of going over 6 x's. So it's like you did that 15 minus 3, and you're like, hey, I went up 12. My y's changed by 12. But over the course of 7 minus 1, 6 x's. Okay? And over here, you're like, here, I went up 4. Yeah, that's the same thing. But I went up 4 over the course of 1x. How can you compare the two in terms of like an apples to apples basis? Like, what can I do with those numbers so that they're equally comparable? You can divide them. And if you divide them, you can simplify something on a y's per x basis. I'm going up 2 y's as I go over 1x. Here, divide them. Well, it's already simplified, telling me I'm going up 4 y's on a per x basis. And I would say, well, there's more change here. What did we just calculate? The S word, slope. Slope. My friends, and you can put this on the bottom in big, 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 big letters. Slope. Give us a per x rate of change, a rate at which things are changing. Rate means like per 1 unit. Slopes are change. You guys know the slope formula, right? Take your y's, divide them by the x's, you get a y per x. Okay? But the problem is, functions, they don't just like go up nicely. You don't connect these nicely. They go up and down and stuff like that. Okay? So like here's where these points come from, this function f of x. Even though this function's going up and then down and then back up, if I took the point at 1, 3 and put the point at 7, 15, connected them with a line, found the slope of said line, I'd be finding the average rate at which the function's changing. There we go. So the function's going up, the function's going down, it's going up. It's like increasing like quicker, decreasing kind of quickly, it's going up. But we can say, hey, well, on average, if I find the slope here, the slope will give me the average rate at which the function's changing from this point to that point. This slope, too, gives me this statement. Even though the function's going up and down and up, I would say, on average, my function is going up 2 y's per x when x's are between 1 and 7. Okay? Slopes of lines connecting 2 points of a function are called the average rate of change of a function. Okay? It's called the average rate of change. We'll use the acronym AROC for average rate of change. Okay? Now, you guys tell me, what is the average rate of change of this function from 2 to 6? I give you the info right here. This is where people start to like fall apart and they're like, oh man, I have no idea what's going on. Here's what you have to start putting in your brain. Slopes equal rates of change. If I ask you to find a rate of change, I want you to find the slope. What are you going to be using? The slope formula to find the slope. For slope, you need 2 points. You have 2 points. 2, 5, 6, 0. Go. Check your neighbors. What's the answer? Y's over x's. Y's over x's. Y's over x's. Y's per x. Good. Simple. That line connected, its slope, y2 minus y1 over x2 minus x1. You get negative 5/4. You might be saying I went down 5 y's as I go over 4 x's. But you can take this fraction and put it over 1. And it gives you a rate on a per axis basis. You'd say the average rate, this is another way to say this, the average rate of change of the function from x equals 2 to 6 is negative 5/4 y's per x. An arrow. Yeah, x goes from 2 to 6. It's not really proper. Like I've changed it every single time. It's no big deal. It's just we're not too worried about notation. I've got like x equals 1 to 7. I got x goes from 2 to 6. You know, whatever. Okay. All right. So slopes are changed. Slopes are changed. Great. Now I gave you a graph. I gave you the points. What if I give you an equation like x squared? And I ask you, find the average rate of change of the function y equals x squared on the interval x goes from 1 to 4. You should be thinking, oh, I need slope. Okay, slopes. I need y2 minus y1 over x2 minus x1. What are we missing here? What am I missing? The y's. How do you find y's if they're not given to you, but you are given an equation? Tell your neighbors, because this is important. Plug in the x's to find the y's. It seems simple, but a lot of us forget it. A lot of us forget that to get points on a function, if you have an equation, plug in the x's. You'll get the y. Plug in the x's. You get the y. All right, so I need the 2 points, 1, 1, 4, 16. Make sure you subtract your y's and x's in the same order. Instead of saying m, we're going to say a rock. A rock 1 to 4 is 15 over 3, which is 5. We would say the average rate of change of the function is 5 when x's go from 1 to 4. On average, the function goes up 5 y's per x over this interval. It's pretty simple, right? It's not new. But usually with slopes, it's just like, what is the slope of this line? Okay? Well, here where it's like, hey, create a line, find the slope of that line, that tells you on average how things are changing. Now, we're going to call this line something different than just the line connecting 2 points on a function. And it comes from geometry. You guys remember circles in geometry? Do you guys remember what a line that just touched a circle at one point was called? What is it? A tangent line. Okay, so that's called a tangent line. That's not what we're going to call these lines. What was the line that connected 2 points of a circle or passed through 2 points of a circle? What would we call that line? Does anybody remember? Chord is one word for it, yes. But there's a different name that I'm looking for. I actually haven't heard chord in a while. Anybody others? It's an S word. Secant is correct. Yes, secant. This is a secant line. We say that lines connecting 2 distinct points on a function, these are called secant lines. You might be thinking, but Mr. Messer, you go through 1, 2, 3 points of the function, or even more if you keep going. Who cares? Like, we just picked 2 distinct points, we connected them, we call that a secant line. Cool with that? So, the slope of a secant line gives us the average rate of change of the function over an x interval. So that's actually not new. It's a good little reminder. Slopes should change. Fine. What we're going to learn and what we're going to spend the rest of the semester on is the question that baffled mathematicians until like the 1600s, which is, how much is this function changing at one point, at one location, not over an interval, not from 1 to 7, not from 2 to 5, just at 4. Now, let's go back up here really quickly. It's always good to make sure our signs are correct, right? So we know that, like, hey, this is going to be a positive slope. So I want to make sure that this is a positive number, right? Why? Because it's like you go upward from left to right, you say your slope is positive. I'm just going to use that. That's not correct notation, but we'll say that. And like when you drew this line, it goes downward from left to right. You're going to say, oh, that's got to be a negative slope. I get a negative number. We're good with that. You guys cool with that? All right, cool. Now, when we have positive slopes, we say my function's increasing. When we have negative slopes, we say my function's decreasing on average. Is this function increasing or decreasing at this 0.47? Decreasing, okay? Now, if slopes equal change, and slopes of 2 points would equal the average change, it would make sense that the slope at this point would equal the change of the function at that point. Does that make sense? If slopes are change and slopes of 2 points connected is a change over an interval, wouldn't it make sense that the slope right here would be the change at that point? Okay, all right? We're just going to go with that. Well, like, what would be that slope? Would it be a positive value? Would it be a negative value? What would the line look like that would have that slope? Well, it'd kind of be a line that would kind of mimic the function right at this location. And it looks like it would just pass through 1 point. So it's just like, it would be a line right at this point. It would mimic the function, but I can connect and extend it. It creates that kind of line. Cool with that? What do we call a line in a circle that just touches the circle at one location? Kazmierski, stay with me. Tangent line. We're going to call this a tangent line. And we're going to say the slope of a tangent line will give us the change of the function at that location, at that point. Now, we would say, what is the slope? Well, I don't know what the slope is right now, but I know at least it's like a negative number, okay? But this is what mathematicians started with. Like, hey, this is our goal. We want to find the slope of the tangent to figure out how quickly the function is changing at that location. The concept is like understood, it's kind of accepted, but the difficulty is finding the value. Okay? So, they're like, all right, we're going to work on this problem. It took them thousands of years to work on this problem and to get to the answer. Okay, we're going to be focusing our attention on finding a slope of a tangent line because it is baffling. So, skip some stuff. And they said, okay, I need to work on finding the slope of a tangent, which is the change of my function at that location. Okay? The exact rate of change instead of an average rate of change. An instantaneous rate of change you'll see a lot. Instantaneous rate of change versus an average rate of change. Okay? Slope over an interval, average rate at which we're changing over an interval, slope at a point, an instant rate of change, the change at a point. And they're like, hey, we gotta work on this. We're gonna work on this, work on this, work on this. But you know what's annoying? Saying slope of a tangent line, saying instantaneous rate of change. Takes too long to say. Let's come up with a nice little shortcut word, Tina, that we're gonna use so that we don't have to say 4 words at a time or 5 words. Okay? And they're like, all right, let's call this a derivative. You now know what a derivative is. It's a slope of a tangent. It's a rate of change at a point. How do we find it? We don't know yet. We have no idea. But at least we're going to start here. Okay? A derivative is the slope of a tangent. It is an exact rate of change because slopes are change. Cool? This summarizes what we just kind of learned. You got a secant line. The slope is the change over an interval, the average rate of change. This is a tangent line. The slope is the change at a point, the instantaneous rate of change. We're good on this. Slope formula, no problem. But this, no idea right now. Okay? But we're actually going to find a derivative right now using a calculator. Okay? We're going to find a tangent slope right now using a calculator. We're going to start with this function x cubed minus 2. If you don't have a calculator, it's okay if you don't have a calculator. I have a calculator. I'll show you everybody. All right, and I'm going to be a little bit exaggerated with the sketch of x cubed minus 2. Okay, we are going to focus our attention right here at this point. What's the y coordinate there? Everybody know why the y coordinate 6? Everybody figure out why is the y coordinate 6? Good. You plug in 2, you get the y. It's cool. All right. So I am going to try to find the slope of this line. Need to be a little bit more exaggerated. Cool. Okay. Well, it's like all you guys know about slopes is the slope formula. The slope formula, y2 minus y1 over x2 minus x1. What's the problem with the slope formula in this situation? Oh, well, 1 point. I need 2 points to use the slope formula. And it's like, well, can I plug in this point twice? 6 minus 6 over 2 minus 2. No, I can't do that. Yeah, that'd be great. So, problem at 1 point, just right there on that pile. Problem is I need 2 points. All right, well, let's start with just 2 points, maybe that like are surrounding 2. Let's start with a point at 1 and a point at 3. If you go up to the top of the page, I ask you, hey, what's the average rate of change of the function from 1 to 3? All right, go ahead and do this. You can do this without a calculator. You don't need a calculator for this. But then I'll have a calculator to do maybe the next thing that we're about to do. Go ahead. You all should be able to do this. Ready, set, go. Average rate of change. Slope, you need y2 minus y1 over x2 minus x1. For the x's 1 to 3, these are x's. What are you missing? You're missing the y's. You need to find the y's. Find the y's, do the math, check with your neighbor. Hurry. No. 1 to 3, not 1 to 2. Your 3's wrong. What is it? Get the answer. Get the slope. That's what I'm asking you for, the average rate of change. Y2 minus Y1, be careful. I see a lot of different answers out there, so let's make sure we're getting the right answer. Good. Yeah. Good. No. No. Yes. Everybody look at Fitzsimmons. She knows what she's doing with her slope formula. We good over here? What'd you get, youngling, in the corner? Don't worry about the 2. Cross out. I just want 1 to 3. I like that idea, though. But let's go with it. I really like, actually, what you just did. Okay, so I want the point at 1. I get 1 cubed minus 2 is negative 1. So I have my first point, 1, negative 1. My second point at 3. 3 cubed is 27 minus 2 is 25. So my second point is 325. You just plug it in to find the average rate of change over the interval 25 minus negative 1 over 3 minus 1. You get 26 over 2. Many of you need to practice using your slope formula when you do your homework, because too many of you got that wrong, okay? All right, so we got a slope from 1, negative 1 to 3, 27. It's up there. And I got that the slope here was 13. Now, I wanted this to be a little bit more obvious, so I'm going to change something really quickly just to make sure that 2 is between 1 and 3. Okay, cool. Now, my goal is to find the slope of this line, all right, at this one point. Would I say that the slope is around 13? Would you feel comfortable saying that the slope is around 13? Would you say that 13 is a good approximation for the slope of that red line? Tell your neighbors. What do you think? I mean, if you just look at the two lines, ready? If you look at the two lines look to be very similar in terms of their pitch. So I'd say this slope is probably close to 13. All right, cool. Well, let's pretend you all have a calculator out. Just right on my computer. Let's pretend you all have a calculator, okay? And with a calculator, you know, you can use whatever point you want. You don't have to stick with whole numbers, right? You can plug in x coordinates like, I don't know, 1.2, and your calculator will quickly give you the y coordinate there, okay? Okay. Let's use 2 points that are probably decimal, get their y coordinates using our calculator, and use the slope formula with those 2 points. What 2 points would you use so that you would get something that you would feel like is a great approximation? Which 2 points would you use where if you found the slope of those 2 points connected, you'd say that's got to be really close to the slope of that red line. Ready? Go ahead. Talk. Discuss. Yeah, right? Why not use points really, really close to x equals 2? Right? Why don't we use 1.999, we'll start with 1.99, and 2.01, and find the slope using those 2 points. Because it's 2 separate points, I'm going to be able to use the slope formula. Now, what is that concept that you guys just thought of? What made you think of that? What did we learn last? Okay, limits, right? Going close to things. Okay, so we are combining a slope formula, which we already know about, and then something we just learned about limits. We're going to combine slopes and limits. Okay, cool. All right, so here we go. Let's get into the calculator here. Let's go into the home screen, and I'm going to do that math. Obviously, the y2 is like 1.99 cubed minus 2, or that's the y1, and the x1 is 2.01 cubed minus 2, right? And whatever that value is, let's just, we don't have to get it, because I could just plug it straight into the slope formula like that. 2.01 cubed minus 2 is the y2, minus 1.99 cubed minus 2 is the y1, and then I divide that by 2.01 minus 1.99. And we got that the slope, or the average rate of change, really, from 1.99 to 2.01 is 12.0001. Cool. But you guys didn't say 1.99 and 2.01. What did you guys say? You guys said, no, Mr. Messer, you should be using 1.99999. You should be really, really close to this location. A little bit to the left and a little to the right, right? So this isn't close enough. You guys are like, hey, let's use 1.999, 2.001. And I went ahead and did that. And I got 12.000001. So this average rate of change, good approximation. This average rate of change, better approximation. If we kept getting better and better approximations, we would approach the instantaneous rate of change of this function at 2. What do you think we would get? Yeah, boom, you just found your first derivative. Congrats. You just found your first derivative. You found the slope of x cubed minus 2 at x equals 2. How did you do it? The slope formula. You guys know that. And your newly acquired mastered concept of the limits. Combined derivative. Slope, limit. Yeah, I'm not super satisfied with how we just did that. I mean, that's the right answer. But what do we use to get it? Did they have calculators back in the day? No, they didn't. They didn't have calculators back in the day. So guess what, guys? This process, using a calculator, going to the right, to the left, let's keep that in mind. Slope formula, limits, we'll keep that in mind. But we need to get this number 12 a different way. Because this is not a realistic process if we don't have a calculator. We got to start over. But at least I have something that I know I want to get, because I have found my first derivative. I found the slope of x cubed minus 2 at x equals 2 is 12. But for the rest of class, we need to find this without a calculator. Okay, cool? All right. Well, what's a good place to start if you're given a math problem? You have no idea where to start. Graphs, sometimes visualizations help. Cool? All right. Let's visualize that number 12 somehow, some way differently, okay? So here is the graph of x cubed minus 2. Cool? And here's x equals 2, right? X equals 2. Well, here was that line. This is a different scale, so it's a little bit different. There's a line. I'm just going to do a little segment of it. And we found that this slope was 12. Right? You know what I'm going to do? I'm going to take that slope value of 12, and I'm going to plot that as a y-coordinate over 2 on this new graph. This is the graph of tangent slope values. So if this is x equals 2, I'm going to say let's plot a y-coordinate of 12. You guys got that? Cool. Well, like, let's pretend we didn't have a calculator. If we didn't have a calculator, we wouldn't know that this is 12, right? But what do we know? That this is a positive slope. So at least we could say, well, like, I might not know what the value is, but, you know, it's positive, right? It's above the y-axis, so this is a good place to put it, okay? Now, our goal is to find out some way to figure out that this location's at 12. All right, well, let's see what the other tangent slope values would be. Now, the problem is I don't have numbers, but at least I can see, based on their slopes, whether it's positive, negative, or 0. It's right there, right there, right there. Okay. Now, at x equals 1, is the slope of this line positive, negative, or 0? Tell your neighbor. Now, would you say its value is equal to 12, more than 12, or less than 12? Tell your neighbor. Less than 12. Okay. Well, pretending that we don't know that this is 12, we would know at least that this is less than that one. So if this is up here, I would say right here, my slope value, whatever this y-coordinate is, it's less than this slope value. Okay? Okay. Do it for the remaining 3. At 0, at -1, at -2. Plot the slope value of f at 0, at -1, at -2. Tell your neighbors, it's like, okay, I got this one is this is this, and this is this. I think I should plot them here, here, and here. Okay, ready, set, go. Good. Now compare the two positives here. Which one would you say is bigger than which one? Okay, so that means this y-coordinate above -2 needs to be higher than that y-coordinate there. Good, Rodriguez.
That's right. But I got positive.
What is that slope right there? Isn't it the same or similar as that one?
Yes.
Didn't you say this is positive?
Yes, that's right.
Well, I mean, just plot the points for right now. Let's just start with the point. Okay, you guys got to get used to doing this because we will be doing this. It is something required for you to do, is to visualize slope by creating these tangent slope value graphs. You got to remember that lines going up from left to right, slopes are positive. This is another way of saying positive, or I can just say plus. Lines going down from left to right, the slopes are negative. Lines that are horizontal from left to right, the slopes are 0. Depending on their pitch, their steepness, we can either be more positive or more negative. Okay. This slope is 0. So at 0, I plot the slope value of 0. This slope is positive. It's a very similar slope to this slope, which was positive. So at -1, I have a positive value that's close to this value. at -2, very similar to this slope's value at 2, which is very positive and steeper, which means it's a bigger positive. Okay, what do you guys want to do with those points? What do you want to do? When you guys see points that look like that, what is your instinct telling you to do? I really want to connect those, right? Let's just make sure we can, okay? Let's look at -1.5. All right, look at -1.5, the slope right here, and tell me, does it fit in between these 2 points? Yes, no? Let's think about it. Here's the slope. It's less steep than this, but steeper than this. Yes, it does. What about at -0.5? What about at -0.5? Is it going to fit in between? Yep. It's less steep than this, but it's positive, so that fits. And it would do the same thing on the other side, which means, guess what? We can connect. Because if we kept doing that experiment, we'd find an infinite amount of points that would lie on what may be an absolute value, maybe a parabola. I don't know right now. But what I do know is something incredible. That's a graph, right? That's something that's familiar to us. This graph has an equation. Do I know what it is? No. I don't know what the equation is. But, man, these y-coordinates of this graph give me slopes of f. That's brilliant. If I had the equation of this, I could find its y value, right? How do you find y values? You just plug in an x into the equation. And if I plug in this x of 1, whatever this y value is, that's the slope of that right here. If I find the equation and I plug in 2, I'm going to get 12, which is what I found using a calculator. Okay? So that's brilliant. Man, this became the mathematician without a calculator's approach. They're like, let's find the equation for this special graph. It is related to f. It's the tangent slopes of f. We're going to use it a lot. We're going to call it f prime. See this little tick mark? That's not a 1. It's just a tick mark. We call it a prime, f prime. And boy, if I had the equation of f prime, I could use its y-coordinate, and it will tell me the slopes of f. Or I would be able to take 2, plug it in, and I will get 12. This y-coordinate 12 will tell me that this slope is 12. Okay? And we know that's what we get because we have our calculator. But let's pretend we're back in the day where it's like we don't know what that is. But we have a little bit of an advantage because we know it's going to be 12. Okay? So we're going to have to find this equation somehow. That's going to be our goal. But do all tangent slope graphs look like this, like a parabola? You know, let's see. If I gave you a function like x squared minus 2, what would its f prime graph look like? We won't worry about the equation. We'll just worry about the shape. Okay? Go, figure it out. See if you can do it, because you have to be able to do it. The notes are in the back. Oh, if you want to take a one copy. Yeah. Go for it. Embrace this. I know this is new, but you can do this. This is like required of you. Like this is something that you have to know how to do in this class. And if you don't want to try it now, like you may struggle. I like what you're doing. Careful, Irish. sketch little tangent lines. Sketch little tangent lines at these 5 locations. Think about if the slope is positive, negative, or 0, and think about the relative. Careful, doll. Kind of. I wouldn't say they're exact same. Nice, Fitzsimmons. We know this slope is negative. It's going down from left to right. So that means at -2 over here, I want to plot a negative y coordinate. At -1, this slope is negative, but it's a little less negative, right? It's less steep, which means I'm going to, at -1, plot a lesser negative value there. At 0, this slope is 0. So, like, again, I have this point 0, 0. We won't always have that. It's just for these first 2 examples. This slope here looks to be positive, but it's less steep than this slope here, which is positive. So it's like, okay, positive, but then more positive. Okay, it's not always going to be a U. We'll have a very unique graph depending on my original graph. This F prime ends up being a line. If I find its equation, I'll be able to plug in a coordinate, like -1. Find the y coordinate, its location, and that will tell me this number. Cool? All right, let's find some equations. Mathematicians are like, all right, let's find this equation. Let's find F prime. We need some sort of formula that combines what we know. Slope formula, limits. Right? Because you guys instinctually said, let's go a little bit to the right, let's go a little bit to the left. Use 2 points in the slope formula. Boom, you found that number 12. Okay? Like that combined a slope formula and a limit. Okay, let's combine a slope formula and a limit. But it becomes very, very conceptual because they're not going to use a specific function. They're going to just use some random function. And they're going to focus their attention on some random x coordinate to create a formula. Okay, this is them creating a formula. And they're like, okay, well, here's my first point that I'm going to focus on. I want to find the slope at this point x, comma, f of x. And to make things a little bit easy to work with, they're going to say, let's take this second point, and instead of calling it like y or just like x number 2, let's call this h distance away from my first point. So this would be x plus h, which means this y coordinate is f of x plus h. I know it's like, it's conceptual and you're not used to this, but this is what mathematicians had to do to develop a formula to get the f prime equation. Okay, so they started with that, and they started with what they know, slopes are change. They started with the slope formula, y2 minus y1, x2 minus x1. Cool? And they're like, all right, we'll call this point over here my x2 and my y2. I know it's going to look crazy and you guys don't like doing this. You're used to plugging in numbers into slope formulas, but we're going to plug in some stuff. Okay? So here's what my slope formula looks like. And they're like, oh, it's the slope of a secant line, so it's the average rate of change of a function from x to x plus h. And they say, okay, y2 would be f of x plus h. y1, f of x. x2, x plus h. x1, x. Is this slope formula, does it look scary? Sure it does, but don't worry about it. We understand it's the slope formula, right? The slope formula of 2 points h distance away from each other on an x-axis. Now, what do you see that you'd want to do? Cancel the x's, right? Because like x2 minus x1, like the x's cancel. You just have that h distance. That's the change in x's. All right, so they're going to simplify that. And now this is where people kind of lose the fact that this is still a slope formula. This is slope of 2 points h distance away from each other on the x-axis. They're like, great, that's the average rate of change. And they're like, well, we still need 2 points, but what we want to do is put those 2 points really, really close together. So they want to take this point and put it practically next to the other point, just like you guys did by using 1.99999 and 2.0001. You're like practically on top of each other, all right? So when I do that, like my line goes from secant and turns into a tangent line, it gives me better and better and better approximations. Well, if you keep getting better approximations, you will eventually get to the actual value, right? Okay, what did they change? They changed h. And they're like, hey, when these points get closer and closer together, what's going to happen to h? Tell your neighbors. Good. What value is h approaching? 0. 0. The distance is h. The distance between the 2 points we want to approach 0. So they use the slope formula, and then they used what was newly discovered by them, the concept of a limit. And they said, hey, find the limit as h approaches 0 of this. And they just discovered a formula to find the equation of those f prime graphs that you just sketched. Yeah, it's messy. It doesn't look pretty, does it? But what is it? A combination of a slope formula and a limit. It's the slope of 2 points, h distance away. Well, if h approaches 0, it's the slope of 2 points infinitely close together, like you guys doing a 1.99999 and a 2.0001. Okay, got it? So a combination of two things you already know how to do. Boom. Now there's an alternate way that they did it, which isn't as helpful because it doesn't give us equations, but will give us slope. And I'll quickly kind of show you. They said, hey, if this was c and this was x, this would be f of c, this would be f of x. They said, take your 2 points and make x be really, really close to c. So they said, well, this point is x f of x. This point is c f of c. They did f of x, y2 minus y1 f of c over x minus c. Again, that's just 2 points. This is just slope formula. But if you combine that with a limit, you turn this into the slope of a tangent formula at a specific location c. Okay? This is the definition of a derivative. It's the combination of slope formula and limit. To say, do you want a tangent slope equation, which will then produce tangent slope y values? You can either use this formula, which you actually won't be using, but you'll have to know what it is, or this formula. No, but you have to know what it is. Both of them are tangent slope formulas. These are tangent slope formulas. It's slope and a limit combined to be tangent slope. And like right now, we just like it feels like we took a huge tangent to something completely different. But remember, what was our goal? Our goal is getting this number 12, which is the slope of this, by finding an equation for this. And in that equation, hopefully I'll be able to plug in 2 and get 12. Cool? All right. Well, I'm about to do that. I'm about to find your equation for f prime when f is x cubed minus 2. Now, don't copy this down, because for your homework, I'm going to be like, hey, I use the magical formula, here's f prime, and you just need to know how to use it. So all these steps that I'm about to show you, just like, I'll show you why it's like kind of complicated and why we won't be doing it because it's so complicated, how there's going to be other things we're going to do using the magical formula that'll get us what we're looking for, okay? So for right now, let's just go with it. All right, so I'm going to try to find this f prime formula using my combination of slope formula and limit, which is the definition of a derivative. Cool? And it's like, well, how the heck do I use this? Well, it's actually not that bad. Like, I know what f of x is. I'm going to replace it with x cubed minus 2. What the heck goes here? It's like, well, I can write down what x plus h is. Instead of x, I have x plus h. So I'm actually going to take that and plug it in here. Okay. Here we go. I got a limit as h approaches 0 of x plus h cubed minus 2 minus the quantity x cubed minus 2 over h. I'm going to move back so I'm all not crooked. All right, great. Now, again, you guys shouldn't worry about this. Just I'm showing you why, like, you won't have to worry about it because it's actually kind of complicated and algebraically complex. So what do you want to do here? Well, like, I want to be able to plug in 0 for h, but I would get 0 over 0 that's bad. So I'm going to just, like, try to simplify this a little bit. I'm going to cube x plus h. Now, I don't know if you guys remember from maybe Algebra 2 or other math classes, like how to cube things, but you get x cubed plus, like Pythagorean triples and stuff, 3x squared h plus 3xh squared plus h cubed. I meant Pascal's triangle, not Pythagorean triple. Minus 2. Then I'm going to distribute this negative. So this is negative x cubed, and this is plus 2. Cool? All right. Why did I do that? Just because. Do you have to worry about doing that? No. Just I got to show you how I get it instead of it being magic, okay? I don't want to just go straight from here and be like, hey, magic. How'd you get there? Oh, I used the magic formula. Like, I'm showing you. Okay, cool. X cubed minus x cubed. Oh, look at that. That goes away. Negative 2, positive 2. Oh, look at that. That goes away. Every remaining term has an h. I'm going to factor out said h. Okay, so if I factor out the h, it's kind of like I'm going to remove a removable discontinuity. After I cancel this h with this h. Oh, look, gone, gone, right? Giving me kind of like my f star that I can now plug 0 into. If I plug 0 in for h, I get 3x squared plus 0 plus 0, which is 3x squared, which is that. Now, in the future, you guys will be able to go from f to f prime like that, because I'm going to tell you rules that were developed using the magical formula. You guys don't have to worry about that. But what you need to understand is, what is this? What did we just find? Flip back to your notes to the point where you're like, oh, we just found this. What did we find? This is important. No. Yes. What I just found was this graph equation. What did we find using our calculator that I wasn't really comfortable with? That the slope of x cubed minus 2 at x equals 2 was 12. We used our calculator, we got that. I said, well, guess what? That's not realistic. We can't use a calculator always. Can we now get that value 12 without using our calculator? Yes. Booyah! Plug in 2 into f prime, you get the number 12, you get this y coordinate, which means you get this slope. All right, fancy pantsers. What is the slope of this point on x cubed minus 2 when x is 1? What is this slope right there? Tell your neighbors. At 1. What is it, little? It's 3. Wait, how'd you get that so easily? Did you use 1.001 and 0.999 in a calculator? No. You use this equation whose y coordinates give you slopes of f. You want a tricky one? What's the slope of this line segment here at -0.5? Turn it into a fraction, and then give me a nice fraction. You could plug in values and y coordinates of f prime give you slopes of tangents of f. So plug in -0.5, you get +1/4 times 3, you get 3/4. Guess what? Boom, that slope right there, 3/4. This is the magical discovery that took until the 1600s to find. That you want to find slopes of tangents? Get an equation to help you. Where does the equation come from? A magical tangent slope formula that combines a slope formula and a limit. Now, let me show you what I'm going to tell you to do. Let's go to this one. If you don't have it, whatever. Let's look at f of x equals x squared minus 2. Okay? That is this graph right here, x squared minus 2. And let's look at x equals 1. Okay? X equals 1. And actually what we're going to do is find an equation of a tangent line. All right, here's what I would do for you guys. I'm going to say, hey, I use the magical formula f prime of x equals the limit as h approaches 0, which is f of x plus h of f of x plus h minus f of x over h. I use this magical formula for you. I did all the work for you. And I'm telling you that f prime of x is 2x. And I'm going to ask you, what is the slope of the tangent to this at x equals 1? Yeah, you got it. 2x is this graph. You plug in 1, you get the y coordinate 2, that's that slope. Oh, and you know what we can do? Let's have some fun with this. let's visualize what we just discovered. Let's write a tangent equation. Okay? So tangent line equation. You're going to do this so often. I hope you're paying attention. Now, you guys remember the generic formula for an equation of a line? Y equals, sure, that's nice if you know what the y-intercept is. Do you remember a equation that just used a point and a slope? Because what I'm talking about here is I want to find this equation of this line at this point. Anybody remember it? Nope. No. Y minus y1 equals m times x minus x1. My friends, commit this to memory. This is the point slope form of a line. Now, here is x squared minus 2. Here's x equals 1. What was the slope of this line, and how did we find it? It was 2. How'd you find it, Farnworth? Yeah, from this magical equation, you could plug in 1, you get 2. That's like the graph of the tangent slopes. So the y coordinates of f prime give me the slopes of tangents of f. Okay, so we got 2. What is the point on my graph? What's the point on my graph? Not 1, 2. How do you get points on graphs? I found a point on the f prime graph. I plugged in x and I got a y. This y is a slope. Use the original equation. Plug in x, get a y. We have a point on the graph. F prime's y's are points on f prime that give us slopes of f. That's really fancy. That's nice. But don't forget, you can plug in x into the original equation and get y. So I got a slope of 2. I got the point 1 comma negative 1. All right, y minus negative 1 equals m times x minus 1. You just developed your first tangent line equation, which I'm going to graph to show you how awesome it is. This is plus a positive. I'm going to just subtract 1. Don't even worry about solving for mx plus b. Just leave it in this form. All right, ready? Here we go. We got y equals x squared minus 2. And I got 2x minus 1 minus 1. Here is y equals x squared minus 2. And there is the tangent line. Isn't that nice? Okay, well, let's go back to our original question. X cubed minus 2 and x equals 2. Now, we did all the work. I did all the work. But when I did all the work, I found the equation of the tangent slope of f. F prime was 3x squared. Give me the equation of the tangent line that we've been focusing our attention on here at 2. I'm not going to give you the y coordinate. Whose slope we know, but maybe you've forgotten, you could find.
Joe, what's good, Zach?
Shut your face! Sorry. I like to yell at people in the hallway. No. You got a point right here. You got a slope. I'm not giving you anything, but you can find everything you need. Ready? The point is at 2, 6, right? How do I know that? Well, I can plug in 2 into F, and I'll get points on F. The slope is 12. How did I get that? Well, plugging in 2 into F prime gives me points on F prime, but points on F prime, y's of F prime, are slopes of F. This is the slope of F at 2, 6. Y minus 6 equals 12, x minus 2. Solve for y by just adding 6. You won't have to solve for y at all. If you just leave it like this, this is fine. Here we go. X cubed minus 2. 12. X minus 2 plus 6. There's the graph. There's that tangent line. Okay? Let's try one more. You know what? Let's combine the two. X cubed plus x squared. I don't know what it looks like. But I used the definition of a derivative. I did a lot of work for you. And I found that its f prime graph is 3x squared plus 2x. I found that for you. Tell me, what's the slope of the tangent at x equals 1 to x cubed plus x squared? Tell your neighbors. What's the slope of the tangent to x cubed plus x squared? You didn't even know what it looks like. What's the slope of the tangent? 5 is correct. Why? Plug in x's into f prime. Y's of f prime give you slopes of f. What's the equation of the tangent line? Y minus y1 equals m times x minus x1. Your y1 comes from the point on f, which is 2. Okay? Yes, this is new, but you got it. F prime is the tangent slope generating equation.
Bye, thank you.
You won't use the magic formula at all, but you got to know what it is. All right.
I'm working.